Hi friends, in the myself Santosh Bagal. In the last lecture, in the part first, we have discussed what kind of singularity of an analytic function. There are three types of singularities: removable, essential, and pool. These are the singularity of a given function. Also, we have seen what kind of theorems are there. By using that theorem, we can easily see which singularities are there. We have seen 9 theorems related to these singularities. Also, we have seen test for detecting singularities. Okay. In this lecture, we will solve some example which are asked in CSIR net. Okay. Let's start. Example 1. At example 1, at z is equal to 0, if z is equal to z upon z cube has, there are 4 options. First option is a pole of order 2, pole of order 3, removable singularities, essential singularities. Okay, these are the 4 options. See, here, if we put z is equal to 0 in the denominator, what do we get? Denominator becomes 0, and on the numerator we get e raised to 0, means 1 upon 0 is infinity. So this function has at a point z is equal to 0 is a pole. Okay. In pole there are 2 options: pole of order 2, pole of order 3. As we have seen definition, if there exists a positive integer m such that limit z tend to a, z minus a raised to m into fz exists, then we say that that function fz has pole of order m. So here pole of order 2, consider option number 1. Pole of order 2, take z minus 0 bracket square. So we can write simply z square. Multiply z square into this fraction. What do we get? Z square into fz is equal to z square into z square e raised to z upon z cube. We get e raised to z, z square cancel, we get e raised to z upon z. If we apply limit z tend to 0, e raised to z upon z, again it becomes infinity. That limit does not exist. So we cannot say at point z is equal to 0, this fz has a pole of order 2. Take this, we are taking z cube, z minus 0 cube, because in option 2, option is what? Pole of order 3. So we take z cube, multiply to this function. What do we get? Z cube into fz, we get e raised to z. Apply limit z tend to 0, z cube fz, nothing but limit z tend to 0, we get answer 1. That limit is finite, that limit is exist. So option is pole of order 3. Getting me? What I am used here? Now we have to use a simple definition of pole of order m. Suppose we are having function fz and z is equal to a is a singular point of fz. If there exists a positive integer m such that limit z tend to a, z minus a raised to m into fz exist, then we say that that function has at z is equal to a pole of order m. Okay, by using definition. Okay, which option is correct? Option 2 is correct. Now move to the second question. What is second question? Singularities of fz is equal to z square upon e raised to z4 are: first option removable, second option essential, third option pole, and fourth option none. See here, first we have to find a singular point of this function. Okay, see on the denominator, here e raised to z raised to 4 is a function. Okay, e raised to z raised to 4 function, and if we equate to 0, which is impossible, okay, for any value of z, that may be real or complex values. So denominator this function e raised to z raised to 4 never 0 for any real or complex values. It never 0. So this function has no singular point. So there is no need to go further that singularity is removable or initial or pole. This function has no singular point. So which option is correct? For this question, option 4 is correct. None is option of this question. Getting me? Next. Question number 3. At z is equal to pi by 6, fz is equal to 1 upon 2 sin z minus 1 bracket square has, there are 4 options. Option 1 is what? Pole of order 2. Option 2, pole of order 3, removable singularity. And option 4, essential singularity. Okay. See, if we apply limit z tend to pi by 6, see on the denominator, what do we get? 2 into sine pi by 6 minus 1. Sine pi by 6 is 1 by 2. 2 into 1 by 2 minus 1. 1 minus 1, 0. Denominator becomes 0. 1 upon 0 is infinity. So this function has at z is equal to pi by 6 pole. We have to check which type of the singularity are there. Okay. So here, if we apply limit z into pi by 6, we get fz tend to pi by 6, fz tend to infinity. So this function fz has pole. Now we have to find. We have proved that here this function has at z is equal to pi by 6 is a pole. So this option C and D option are wrong options. Now we have to check what is the order of that pole. Okay, so first multiply this fz by, because here option A is what? Pole of order 2. So multiply fz by z minus pi by 6 bracket square. Okay, and find that limit. What do we get? Limit z tend to pi by 6 z minus pi by 6 bracket square into 1 upon 2 sin z minus 1 bracket square. If we apply limit, we get 0 by 0 form, means indeterminate form. Apply Euler's rule. What do we get? Limit z tend to pi by 6, take derivative of numerator on numerator, write on numerator, take derivative of denominator, write on denominator. What do we get? Limit z tend to pi by 6 to z minus pi by 6 upon 2 into 2 minus 1 into 2 cos z. Again apply limit. What do we get? 0 by 0 case, again indeterminate form. Okay. Next, again apply Euler's rule. What do we get? Limit z tend to pi by 6, 1 upon 2 sin z minus 1 into bracket minus sin z plus cos z into 2 cos z. If we apply limit, we get a limit as 2 by 3. That limit exists. Okay, so we can say this function fz 1 upon 2 sin z minus 1 bracket square has a pole of order 2 at a point z is equal to pi by 6. Okay, you can do this calculation on rough page. Take rough page, take pen and do this calculation. We have to simply find limit z tend to pi by 6 into z minus pi by 6 bracket square into 1 upon 2 sin z minus 1 bracket square. We have to solve only this limit. This limit, after solving, we get answer as 2 by 3, which is a finite. That means that limit exists. Okay. So this question, which option is correct for this question? Option A is correct. See next, question number 4. At z is equal to 0, at z is equal to 0, fz is equal to e raised to z upon e raised to 1 upon z minus 1 has. Okay. First check. If we put a limit here, what do we get? E raised to 1 upon 0. Here, that limit does not exist. If we apply limit on the denominator, that limit does not exist. Okay. So, we have to find, we have to use that 9 theorems. Out of that 9 theorem, we are using a theorem here. the limit point of the sequence of poles is an non-isolated essential singularities. Okay, for that we have to find pole of this function. In order to find pole, we are putting denominator equal to 0. What do we get? Do this calculation on page. Take denominator, do denominator equal to 0. E raised to 1 upon z minus 1 is equal to 0. This implies e raised to 1 upon z is equal to 1. Taking log on both sides, what do we get? 1 upon z is equal to I into bracket 2k pi. K is an integer, that means positive or negative integer. So finally get pole of this function has z is equal to 1 upon 2k pi I. Okay, k belongs to positive integer or negative integer. Okay, what are the poles of this function? Pole of these functions are z is equal to 1 upon 2k pi I. Okay, these are the sequence of the poles of this function fz. If we find the limit point of this sequence, what do we get? Limit point of the sequence is what? 1 upon 2k pi I. 2 is constant, pi is constant, I is constant. Okay, if we apply limit k tends to infinite, 1 upon 2k pi I, we get value as a 0. Okay, and we have to check at which point? We have to check at z is equal to 0, which type of the singularities. If we find a limit point of the pole, we get a limit of sequence of poles as a 0. So by using that theorem, the limit point of the sequence of the poles is a non-isolated essential singularities. So this sequence of pole has a limit point 0. So at point 0, this function has non-isolated essential singularities. So for question 4, fourth option is correct. Now see, on question number 5, we have to check at point z is equal to 0. Here fz is equal to what? Cos z square plus 1 upon z square. Okay, there are 4 options: pole, essential singularities, removable singularities, none. Okay, see, first I apply limit, check whether it has a removable singularity at the point 0 or not. Okay, as you know definition, suppose we are having function fz, we are checking the singularity at the point z is equal to a. What is the definition of removable singularities? Limit z tend to a, if z exists finitely, then we say that that point a given function has a removable singularities. If there exists a positive integer m such that limit z tend to a, z minus a raised to m if z exists, then we say that this function at z is equal to a polar order m. If singularities other than pole and removable, we say that we can say essential singularities. So first let's check whether limit exists or not. Apply limit z tend to 0, f z is equal to cos 0 plus 1 upon 0. Okay, so limit does not exist. Getting me? Cos 0 plus 1 upon 0. 1 upon 0 means what? Infinity. Cos infinity does not exist. So limit z tend to 0, f z does not exist. So this function has essential singularities. Getting me? Limit does not exist. If limit does not exist, then we say that point given function has a essential singularities. See example number 6. What is example number 6? At z is equal to 0, if z is equal to z upon e raised to z minus 1 has. Which point is a singular point? If we put z is equal to 0 in the denominator, what do we get? E raised to 0 minus 1 means 1 minus 1. Denominator becomes 0. Okay. So denominator becomes 0, but see here on the numerator there is a term of z. If we put z is equal to 0, what do we get? 0 upon 0, which is indeterminate form. Apply limit z tend to 0, f z is equal to limit z tend to 0, z upon e raised to z minus 1. What do we get? 0 by 0, which is indeterminate form. Apply L'Hospital rule. What do we get? Limit z tend to 0. Take derivative of the numerator on the numerator. Derivative of z is 1 upon e raised to z. Again apply limit. Limit z tend to 0, 1 upon e raised to z. What do we get? 1 is the limit. Okay. We arrived at limit z tend to 0, f z is 1, which is exist finitely. So this function has a removable singularity at a point z is equal to 0, because a limit exists at a point z is equal to 0 by applying 2 times L'Hospital rule. Okay, so this function fz is equal to z upon e raised to z minus 1 at point z is equal to 0 is a removable singularities. Okay, see question number 7. At z is equal to 0, fz is equal to 1 minus cos z upon z square has same type. We have to solve example as we have solved example number 6. Same way we have to solve example number 7. Okay, see, apply limit z tend to 0. What do we get? Limit z tend to 0, fz is equal to limit z tend to 0, 1 minus cos 0, 2. Cos 0 means 1, 1 minus 1 upon 0, 0 by 0, which is indeterminate form. Take, apply L'Hospital rule. What do we get? Limit z tend to 0, derivative 1 is 0, derivative of cos z is minus sin z. With minus sign, what do we get? Plus sin z upon 2z. Again apply limit. What do we get? Limit z tend to 0, sin z upon 2z. We get 0 by 0 case. Okay. Again apply L'Hospital rule. What do we get? Limit z tend to 0, cos z upon 2. Apply limit. We get 1 by 2, which is a finite quantity. So limit z tend to 0, fz exists finitely. So this function fz has at z is equal to 0 removable singularities. So for question 7, option C is correct. See question number 8. Function given here, fz is equal to e raised to 1 by z. We have to check at the point z is equal to 0. Check limit, find first a limit z tend to 0 fz. What do we get? Limit z tend to 0 e raised to 1 by z. Limit z tend to 0 e raised to 1 upon 0. Limit does not exist. Directly we can see. So limit does not exist. So we can say function fz is equal to e raised to 1 by z has at z is equal to 0 essential singularity. You can use other technique also. What is the other technique? Find Taylor series expansion or Lorentz series expansion of function fz is equal to e raised to 1 by z. Okay, what do we get? As you know, Taylor series expansion of e raised to z. What do we get? E raised to z is equal to 1 plus z square upon 2 factorial plus z cube upon 3 factorial plus and so on. Replace in place of z by 1 by z. What do we get? Expansion of e raised to 1 by z. 1 plus 1 upon z plus 1 upon z square into 2 factorial plus 1 upon z cube into 3 factorial plus and so on. So this is the Taylor series expansion of e raised to 1 by z. Also, you know, definition of pole, removable singularity, essential singularity in terms of principal part. If suppose we are having function fz, we will find if we find Taylor or Lorentz expansion of given function fz. There are two parts in that series. There are two parts. One part is the analytic part, and other part is principal part. Depends on that principal part. We can say that function has which type of the singularities. In the principal part, there is no term. In the principal part, there is no term of the given function. Okay, in no term. So we say that that point given function has a removable singularity. In the principal part, there are finite number of terms. So in that case, we can say given function has at a point pole. If there are infinite number of terms in the principal part of Taylor series or Lorentz series expansion of given function, then we can say given function has that point essential singularities. If we find Taylor series expansion of e raised to 1 by z, there are infinite number of terms of the form 1 upon z. Getting me? So this function has essential singularity at a point z is equal to 0. See example number 9. At z is equal to n, at z is equal to n, fz is equal to tan by z. There are 4 options: pole of order 2, pole of order 1, removable singularity, and none. As you know, tan z nothing but what? sin z upon cos z. Okay, so there are pole involves. First, we find poles of this function tan pi z. Tan pi z can be written as sin pi z upon cos pi z. So poles of this function are given by those values of z that gives values of cos pi z is a 0. That is, poles are given by cos pi z is equal to 0. What are the values of pi z that makes cos pi z 0? That value is nothing but pi z is equal to 2n pi plus pi by 2. N belongs to the positive integers or integers. Okay, if we solve this equation, pi z is equal to 2n pi plus pi by 2, we get z is equal to 2n plus 1 by 2. Okay, now these are the poles of a given function tan pi z. Next, we have to check whether this function has at z is equal to n which type of singularities. Apply limit directly. Limit z tend to n f z is equal to limit z tend to n tan pi z. What do we get? Limit z tend to n sin pi z upon cos pi z. If we put in place of z as n, we get sin n pi upon cos n pi. Sin n pi is always 0. 0 upon cos n pi. Cos n pi is either, because n is integer, so cos n pi is either 1 or minus 1. So 0 upon 1 is 0. 0 upon minus 1 is again 0. So limit exists finitely. So at z is equal to n, f z is equal to tan pi z has removable singularities. Okay, we have to check first whether that point limit exists finitely. If limit exists finitely, we say given function has at that point removable singularities. If limit exists, we get infinite, we say that given function has at point pole. Other than, we say that function has essential singularities. Okay. Number 10, at z is equal to 0, if z is equal to z square into sine 1 by z has, first option, pole of order 1. Number 2, isolated essential singularities. Number 3, removable singularities. Number 4, non-isolated essential singularities. Okay, option 1 is what? Pole of order 1. That means there exists z to the power 1 such that limit z into 0, z into fz exist finitely. Apply, multiply z to this given function. What do we get? Z into fz is equal to z cube into sine 1 by z. If we apply limit z into 0, limit z into 0, z fz is equal to what? 0 into sine 1 upon 0. But sine 1 upon z is not an bounded function. It is an unbounded function. Okay, so this limit does not exist. Limit does not exist. That means this function fz is equal to z square into sine 1 by z has essential singularities. Okay, so option first and option C is a wrong option. Okay, there are two options. First, B option is what? Isolated essential singularities. Option D is what? Non-isolated essential singularities. So we have to check out of these two which option is correct. For that we will find limit point. For that we have to find zeros of this function. What are the zeros? In order to find the zeros of this function, we have to equate to 0. Z square into sine 1 by z is equal to 0. So we get z square is equal to 0 and sine 1 by z is equal to 0. Z square is equal to 0 means z is equal to 0, 0. Sine 1 by z is equal to 0 means 1 by z is equal to n pi, z is equal to 1 upon n pi. These are the zeros of given function fz. Okay, this is the sequence of zeros of the given function. We have to use a theorem. The limit point of the sequence of zeros of a function fz is an isolated essential singularities. What are the zeros? Z is equal to 1 upon n pi. If we apply limit n tends to infinite, 1 upon n pi tend to 0. Okay, 0 is a limit point of zeros of an sequence of zeros of that function fz. So at z is equal to 0, given function fz has isolated essential singularities. Okay, now question number 11. See, this question belongs to the part number C. All remaining questions belongs to the multiple choice question. and this is the multiple select question. See question number 11. Fz is equal to integration 1 to 2 1 upon x minus z bracket square dx. Imaginary part of z greater than 0. Then there is a meromorphic function g of z on C that agrees with fz with imaginary part of z greater than 0 such that, okay, and there are four options. First option is what? 1 comma infinity are poles of gz. Option B 0 comma 1 comma infinity are poles of gz. Option C 1 comma 2 are poles of gz. Option 4 1 comma 2 are simple poles of gz. Do not see on option directly integrate this function. What do we get? Fz is equal to integration 1 to 2 1 upon x minus z bracket square dx. Solve this integration. After solving this integration, we get fz is equal to minus into bracket x minus z raised to minus 1 limit. Lower limit is 1, upper limit is 2. Put a lower and upper limit. We finally arrived at fz is equal to 1 upon 1 minus z minus 1 upon 2 minus z. Okay, this is the rational function, addition of the two rational function. And if we have to check which are the pole, we arrived a function at fz is equal to 1 upon 1 minus z minus 1 upon 2 minus z. So on denominator, there are two factors. First factor is 2 minus z and the second factor is 1 minus z. If we equate to 0 denominator, we get z is equal to 1. Okay, so this function has pole at after finding limit z tends to 1 if z exists finitely, limit z tend to 2 if z exists finitely. Okay, at point 1 and 2 function f z at poles. We have to check whether these poles are simple or not. Simply multiply that function what we have obtained a finally function, multiplied that function first z minus 1, find limit, that limit exists finitely. So z equal to 1 is a pole, that pole is a simple pole. Again multiply that function by z minus 2, solve that limit. Again we get finite limit. So both the poles are simple poles. So among these four options, option C and D correct, because 1 and 2 are poles of GZ, no doubt, but these poles are again simple poles. So option D is again correct. Okay, this is the multiple select question. So option C and option D are the correct option. Okay, solve 12 number and 13 number. These are the homeworks. This is all about examples based on singularities of a function. One thing is important that in order to solve questions related to the singularity of function, you must remember first three things. Simple basic definition of removable singularities, pole and Ischian singularities. After that, 9 important theorem, and after that, test of detecting singularities. These 3 points are very important in order to solve a problem based on singularities of function. Okay, you must remember that function. There is no need of a proof of that theorem. You must remember whenever required. You can apply directly. That gives the which type the singularity of the given function are. Okay, this is all about examples of singularities. Okay, this is the part 2. In order to understand part 2, it is necessary to watch videos related to the part number 1. Okay, if you read part number 1, you can go part number 2. Okay, it is a very easy concept. Okay, this is all about singularitity of the function. Thank you.